In this lecture, we're going to look at sorting. We'll look at a couple different algorithms that implement sorting, and then we'll look at the runtime, a couple different sorting algorithms. So we'll start off here with the definition. Sorting is just arranging a list of items into some well-defined order. For example, that could be putting them in an ascending order numerically, alphanumerically, by birth date. Sorting is commonly used with lists, particularly arrays and array lists. And we know that if we're given a sorted list, that can improve the efficiency of other algorithms. For example, if we have a sorted list, we can use the binary search. And so then we can have a log n search instead of a order n search. So how do you go about sorting a list of items? Well, there are several different methods to doing that, but we're going to step through one approach. It's called the selection sort. And the way it works is we come through our list here and we look for the minimum element, and then we take that and we start that on a new list. So I've exemplified that here on this next slide, where we've got a search going through here, and we're going to come through here and we're going to find our minimum element, which is 1. Once we find that, we take that out of our list and we put that at the beginning of a new list. We then come back through here, we search for our next minimum element, which is going to be 3. We take that out, we add that to the end of our sorted list. We then search for our next minimum element, which is going to be 4, and then we take that and we add that on to the end of our sorted list. So this is what our sorted list looks like after we've moved 3 numbers from our original list down to our sorted list. This here is known as the selection sort algorithm. The steps of this algorithm can be stated this way. Find the smallest element in the list. Add that to the end of a new sorted list. Eliminate that item from further consideration, and then we repeat steps 1 through 3 until all the items in our original list have been eliminated. Here's this word algorithm. So what in the world is an algorithm? It's just a set of instructions for accomplishing some task. You can think of it like a recipe. Please note that we may have an algorithm like we've had on the previous slide, which is very easy to state in English, but it may be a little bit more complicated to actually do that in code. For example, I may have the statement swap 2 values. We can sort of do that in our head, and we know how to do that very simply, but to actually implement that in code, it takes 3 lines of code because I need a temporary variable. If val1 and val2 have values in them and I want to swap those values, so this value in val2 is now in val1, and the value in val1 ends up in val2, I have to create this temporary variable, then take val2, assign it to val1, and then take that temporary variable and assign it to val2. So just because something's easily stated in English, it may be a little bit more difficult to code. What are some of the challenges of implementing the selection sort algorithm? Well, one, it appears that you need a whole extra list to store this sorted list that you're building. And then, how in the world do we go about crossing out items from consideration? That was really easy to do on our little pen and paper technique because we can just cross out the item and we won't consider that, but that's a little bit more difficult to do in code. Well, it turns out that you can actually do this just with a single list and cross out items just sort of by moving forward. So what we can add to this is we've got our starting index of where we're beginning our search for the minimum. So what I come in here and do is I have a starting index, which means starts at the beginning. I go through and I search for my minimum element. As I search for that, when I find it, then I exchange that with my starting index, which is now going to represent my sorted list. So after I exchange it, then I move my start index over. So I'm going to have 2 halves to this same list now. The first half is going to be the sorted. The second part is going to be my unsorted list. So as start moves over, everything to the right of it's still going to remain unsorted. So now I'm going to come through here, search for my minimum, which is 3. Then I will exchange 3 and 4. So it's going to say 1, 3. And the rest of my list will be 10, 7, 8, 4, 6. I'll move my start over, and this will be my unsorted portion of my list. This will be my sorted portion of my list. So we can actually do that without creating a second list And it's not too bad to keep up with what items I have so-called crossed out. How does this end up working? It ends up being a series of passes through my list, where each pass I'm moving over and I'm going to be building this sorted list. I'm going to have to pass through my list the number of elements that I have in my list. But once I've passed through that, I'm going to end up with a sorted list. So the question is, how long does it take? Just as in searching, we're interested in the number of comparisons that we're doing to perform this sort. So in the first pass, we're going to do n-1 comparisons to find our minimum. Then the second time around, because we're going to eliminate one element from consideration, we're going to do n-2 comparisons. We got to end up doing n-1 passes. So how many total comparisons did we did? It's going to be n-1 plus n-2 plus n-3, all the way down to one comparison. If we do a little math on this, if you remember way back probably to algebra class, you can actually sum this all up, and it's going to equal n squared plus n minus 2 divided by 2. Well, what we're most interested in here is this biggest term, which is n squared. So what we say then, that this is approximately an n squared algorithm. So the selection sort is big O of n squared, which is bigger than the big O of n and bigger than log n. But that's how we go about calculating the order of the selection sort algorithm. There are other algorithms to sort a list of items. Just remember, there are always many, many different ways to solve a problem, and some may be a little bit more efficient than others. So we're going to look at another example here. Let's start and say that we already have two sorted lists. So here's list 1 and here's list 2. How would we go about merging already sorted lists? Well, that's actually pretty straightforward. What we can come down here is compare the first element of each list, find out which one is smaller, and then we add that to the beginning of our sorted list. Then we move over to the second item of list 1, which has the value 4. Compare 4 to 3. Which one is smaller? We add it to the end of our sorted list. We move this now over to list 2, so we got 4 and 6. We're now going to compare 4 and 6, so we put 4. And we can continue that process. So if we already have two sorted lists, we have a very simple algorithm to merge those two sorted lists. What about starting with an unsorted list? How in the world can we use that knowledge if we have two sorted lists that we can merge them together? So we can ask ourselves, what size list are you guaranteed to know that it is sorted? The answer would be that's list of size 1. We know that that's an actual sorted list. So we can use that information to begin cutting our problem down so that we can start working with a list of size 1. So this is where we have our list here. We got 10, 4, 1, 7, 8, 3, 6. I'm going to start cutting this problem in half until we can get down to a list of size 1. So now I'm going to break this into a list of size 4 and a list of size 3. I break that in half. I take my list of size 4, break that into two lists of size 2. My list of size 3, I break that into a list of size 2 and a list of size 1. Then I break my list of size 2 into a list of size 1, list of size 2, a list of size 1, a list of size 2, a list of size 1, size 1, size 1. Now that I have broken these down into lists of size 1, I can now start merging those back together. When I come back here, I've got my list of size 1. I take these two lists of size 1, merge them together, so now I have this sorted list. I take these two lists of size 1, merge them back together. These two lists of size 1, merge them back together. List of size 1, merge with this cell, so this size. Now I can take these two lists of size 2, merge them back together, so I get a list of size 4. I take these two separate lists, merge them, produces this list here. Once I have these two sorted lists, I merge those back together, and I come up with the following sorted list. So that's another algorithm to merge an unsorted list. This actually has a name. It's called the merge sort algorithm. And the way it works is we split the list of items into two lists to be sorted. Then we sort each smaller list by breaking it down to two smaller lists, and we keep breaking it down into smaller lists until a list of size 1 is reached. Once we've reached that, we merge each list back into a sorted list all the way back up. And that's called the merge sort algorithm. This here is known as a divide and conquer approach, where we start out and we say, the original problem is too big to solve at once. But I know how to solve it if I can get it down to something smaller. And so we try to break the problem down into smaller pieces, and then we solve each of those smaller pieces separately. And once we have solved those, then we combine those separate pieces back together to build our solution. So this is known as a divide and conquer approach. The merge sort does this by taking our original list, breaking it in half, taking those, breaking it in half till we get down to a list that we know how to solve the problem. That's a list of size 1. Then we start combining these solutions back together to solve our problem. Again, that's a divide and conquer approach. The merge implementation, if you actually had to code this up, it is a little bit complicated, but unfortunately, it's unlikely that you'll ever have to code any sort from scratch, is that we can often usually reference some pseudocode and then implement that ourselves. What's the running time of the merge sort? We sort of do just a wave of the hands analysis. If we divide the problem in half each time, well, we learn from the binary search that's going to take log n divisions. Then to go through and merge each one of those lists, we always know that we're going to have to visit all n elements. So that's going to be order n. So merging the list log n times is going to be n times log n. So it's an order n log n algorithm, which is more efficient than an order n squared algorithm. So I've got some runtime comparisons here, where here's n is the size of our list, the number of elements, and then this is the number of comparisons that we're going to have to do. The red line here represents if it's an order log n algorithm, the green line an order n, the yellow line an order n log n, and then the blue here an order n squared algorithm. If we look here and let's say we have 4,000 elements, log n, we're going to have to visit 12 elements. Order n is 4,000. Here we're probably, I'm guessing maybe 60,000. Then over here we're visiting over order n squared over 10 million elements. If we bump this out to 65,000 elements. Well, if it's an order log n, we have to visit 16 elements, or do 16 comparisons if we're doing a search. If it's order n, of course, we're going to have to visit all 65,000. If it's order n log n, we're going to have to visit right at a little over 1 million. And then if it's order n squared, we're going to have to visit and do over actually it ends up being about 4 billion comparisons. So you'll see here, there's a big difference between these various algorithms. And so with the selection sort being n squared, if we had 65,000 elements, we're going to have to do over 4 billion comparisons, whereas with the merge sort, which is an order n log n, we're going to have to do just a little over 1 million. So there's significant savings with the various approaches. So we always want to try to have the most efficient algorithm possible to be around either order n or order n log n. Now that's not always possible, and it turns out that the best that you can do with a sort, and it's possible to prove this, is to make an order n log n algorithm. I have provided here a link to a web page that shows some visualizations. Here, let me refresh this here, where you can come in and actually see various sorting algorithms working, and it's slowed it down so you can sort of see time comparison. So here I have the selection sort, so I can click that and it's going through each iteration, and I can now compare that to the merge sort, and there's a couple different variations, but let's say I've just started this. So here's the merge sort, and it's quickly going through sorting. The selection sort's still going. Please note, I started the merge sort after the selection sort. It has now gone through. The merge sort is now complete, whereas the selection sort is still going, and that's done. So the selection sort, which is an order n squared algorithm, is much slower than a merge sort. And we know that by just looking at the number of comparisons that are going to occur. But here's a little visualization of that. And we can see some visualizations of a lot of other different types of sorting algorithms. The quick sort is a is another very, very fast algorithm. It's an order n log n, and you'll see how fast that was. That is the end of this mini lecture, and you can read more about sorting in the textbook.